Hello. Good evening, everyone. Welcome to the Quiz 2 revision session for deep learning.
Good evening, sir.
Okay. Okay. So, how was it going? That- are you okay for the content of week 5 to 8? How was it? How are you feeling about that? Where you're facing difficulties?
It's kind of tougher on the tougher side.
Okay. So, which weeks you are facing more difficulty?
Yeah, sir. Just 1 second.
Yeah, others can also may
Yeah,
speak.
the convolutional neural networks week 8.
Okay. What about others? You facing difficult in week 8 or any other week?
The solvers, like
Solvers, optimizers.
the
Okay,
optimizers.
okay. Uh,
For me, it's on the convolutional indexing formula. We have that we have our stride and all, and then we multiply
okay,
our matrix with the error map with our input with the error map. So if we have different type of strides, then how we will be doing that and that formula, the complete formula. So want some revision or some questions if you can solve over that.
okay. Okay, fine. Um, so you have problems in mostly convolution is little difficult. So I think we can start with convolution first, week 8 first. Then we'll move to week 5 and so on. Okay, if that is okay with everyone, we can start. If anything else you want to do, uh, say before the session, before I start, you can tell me. Okay, just let me share my screen. Uh, is my screen visible?
Yes, sir.
Thank you. Okay, so we'll start with week 8 revision. Okay, so so what convolution operation is? I- Somebody's typing. Can you mute? Uh, So whoever is typing, please mute. Okay. Okay. Fine. So week 8 is CNN mostly. It is there. So we'll see what is CNN architecture and what is specifically CNN has two important operations. One is convolution operation, which is actually the convolution neural network name comes from. And another intermediate like operation is there, which is similar to convolution, but it's little different, which is pooling operation. Okay. So So let's say I have some matrix, right? Let's say 4 cross 4, and I have a filter. So this is an image. I would call this as a image or something you can take. If it's a grayscale, okay, that means it's a matrix. 2D 2D matrix is there. Okay, and some values will be there, like 2, 5, something like so 8, something, anything. So generally grayscale images are like you might have seen pixel values are there between 0 to 255. 0 means nothing is there. Like you can say if it's a blank white paper, then 0 is white and 250 is dark black. Okay, so that's how grayscale image works. Right. So that's why some values will be there. Those are image pixel values. Okay. Now, uh, we have this image. If we add some other depth to it, so some depth is there. In that case, we can actually form a RGB image. So what is RGB image is the first matrix is of for red color. Similarly, second matrix is for green color, and then last matrix is for blue color. So if you have this kind of pixels, so this is a 3D image, right? So there is a depth also with height and width. So this kind of images are RGB image, and in this case, we do something different in convolution. So then the filter of this 2D filter will not use, but what we'll use is we will use something like 3D filter. Okay, whatever depth is, we'll always keep depth of our filter similar to whatever image is. So this is like a 2D, this is called 2D convolution. So it's not like the other convolution is not possible. Like for example, I can have 1D, sorry, just a matrix, not a cube, but a matrix kind of filter similar to this, and I can go first layer, then second layer and third layer. I can do that. That is a possibility, but we don't do that. But this is a very popular one, like 2D convolution. We do in that. That is more popular, and we'll see only this variant of convolution in 3D images. Okay, so just remember that whenever the any 3D tensor is there. Okay, so tensor is like 3D. In that case, we'll always use 3D filter also. Okay, so this is a image, and we'll use similar uh, filter, 3D filter with same depth. So same uh, depth is the important part. Okay, so height and width can be different, but depth will be always similar. So if it's not given, then you have to assume that it's a same thing. Okay, and mostly it is not given. So that is the intro to like what is that. Now we'll see what is convolution operation. Okay, so uh, okay, so we have this let's say uh, 4 cross 4 image. Okay, and we have a 2 cross 2 uh, filter. Okay, so this is a filter dimension. Okay, uh, now what we have, let's say I have value 1 2 3 4. Here let me say 5 6 7 8. Okay, so and so on, like so some values are here also. Now I have some values like let's say 1 1 1 1. Just take one. You can have anything. It's a 1 1 1 2. This is my filter. So what you do is you put your filter here. Like let's say you put the filter here. Okay, and then element wise you do multiplication of this. So for example, this multiplied with this here, there, and this one, right? So 1 into 1 plus 2 into 1, so 2 is coming from there, plus 3 into 1 plus 4 into 2. Okay, so this is a convolution operation. So we did it for first one, and let's say 1 plus 2 plus 3, which is 6 plus 8, uh, 14, right? So 14 will be the output of this. So this is a convolution operation, and we got 14. Now what we do is we move. So we move the filter somewhere. So how do I move is I choose some form of stride. So that is called stride. And let's say 1 2 anything I can choose. So stride equal to 1 is, so if I have stride equal to So if I stride equal to 1, that means I'm moving by uh, uh, one cells, right? So whatever this one column or something like that, I'm moving by that much. If stride was 2, okay, so just see that 2 means I would have moved here, okay, not the yellow one. Stride 2 is the blue one, and stride 1 is the yellow one, okay. Equal to 1 is the yellow one. So depends on what stride you choose, you move by that and you do the similar operation, this multiplication. Okay. So nothing changes that. So once you complete it horizontally, then you move downwards of the similar way. So for example, from here, if stride equal to 1 was there, then once I complete horizontally, I come back here. I take this part. Okay, so this is stride equal to 1. So that's why I'll move there and so on. Okay, and then similar thing, I'll move horizontally, complete it, and then I move one step down, and then I go from left to right. So that's what convolution operation is. You do that, and similarly, like once you do that, you write whatever value you get here in this boxes. Because how many, what will be the output size, that we can actually see. So output size, we can we can calculate this. So there is a formula for this. So let's say image width is there something. Okay, so I'll just write W for image width. Then from that you subtract filter size. Okay, so whatever your filter size is. So usually we, most likely we are going to use square filters. Okay, and like, are like rectangle filters possible? It's possible, but nobody uses it. Most of the filters are now it is streamlined that we'll always use square filters for ease of doing it. Okay, so later on we don't have any problem with dimensions. So you will use square filters only. Okay. Now that filter size, whatever that width is, width you can take in this case, that you have to subtract. And something called padding is there in the images. So when we do padding, uh, that that means, let's say I have my image of this, right? So this is my image. I wanted to do a padding of 1. Okay, so one padding means I add zeros around the image everywhere. Okay, so it's like I'm adding zeros. Okay, so basically I'm increasing my image from 4 cross 4 to uh, let's say 4 cross 4 to 5 cross 5. Right, so now it is 5 cross 5, or sorry, it is 6 cross 6.
6.
It is 6 cross 6, right? So I'm increasing it to 6 cross 6. I'm increasing my image. So why it is important is, so sometimes something you wanted to capture from the corners, right? So this is the point where you wanted to capture. But a filter will be like this, right? So initially, if you put your filter will be here, or somewhere like this, like so somewhere like this. So corner things may be important, or you wanted to capture that more time or something like that. In that cases, you add paddings and all, right? So padding has been useful for capturing image corners features. Okay, so that's why we do the padding, and since the size is increased by 2, right? So you can see 4 to 4 to 6, right? So that's why we add 2 times padding into the output size calculation, and then we divide it by strides, whatever stride you choose, 1, 2, 3, whatever you can choose. And we add one extra in this, because it's like it's coming in the formula. If you pay attention to it, you realize that we'll need one more addition to it, and that many bit you will get. Okay, you can manually count it also by moving the filter one by one. For example, I'm moving, let's say, stride equal to 1. First, my filter was okay, let's say my this is my 4 cross 4. First, my filter was here, then I put here, and then third, right? So 3 should be the width of this. If I have 4 of image size, and filter size was 2, so there is no padding. And if I move by style equal to 1, you can see I'm getting 2 as output, which is incorrect, right? So you will require one more uh, additional move to have that correct width size, right? So So that's why this additional one is coming into the equation. Okay, so this is the equation for calculating output size. So we have calculated width using this. You can similarly calculate height also. So height minus filter plus whatever padding you have done, divide by whatever stride you move, and additionally one will be there. Right? So width and height you can easily calculate using this. Okay. So it's fine. You can calculate width and height now. Okay. Uh, okay. Now, what is the parameters? So something like parameters coming into the CNN. So what we do is let, so my image is 4 cross 4, and I use this 2 cross 2 filter. So this filter is all the values in my filter, right? So these 4 values are my parameters. Okay, so all 4 of them are parameters. Now, for our course, we ignore the bias. Okay, so for our course, we ignore the bias, and I would suggest you to ignore the bias. Uh, as of now, we don't need it, but generally per filter there is one bias. So as many filter you use, as many bias you can use. Yes.
Usually, this is the case for like backprop also, right? Like in few of the PYQs, like very previous term, I see like there was a backprop calculation including bias. So is this the case same for now also?
Including bias, so we some. I think the questions in PYQ or whatever previous year, you might see bias in the final output layer, but not in the convolution layers. You can
No, no,
ignore
sir.
it.
Sir, in convolution layer only it was there, sir.
Yes, sir. It was there in one of the PYQ. Very like 2023 maybe. Like
Then you can ignore it. So we'll ignore it for our quiz. We'll ignore it.
okay, sir.
Okay. But yeah. So as of now, you ignore. Okay. Anything else? You have any question?
No, sir.
Okay. Naren, any? Okay.
Same
So
only, sir. Bias was there. That is why I also raised hand.
okay. So as of now, you can ignore it. Okay. We can ignore. So params is parameters are whatever the filter is, right? So filter all the values are parameter. Now these are the parameters which you wanted to update. So whatever this uh, W11, W12, 2 1 and W22, right? So this 4 values as of now you can consider these are parameters, and you wanted to update that, right? So initially when convolution operation started, people were finding filters. What is something like edge selector or edge filter, then something like hog filter was popular, right? So these are the names of filter. So that time the filters values were not getting updated using backpropagation. You apply this filter, you get whatever output in that, and then you pass it through the proper like normal neural network in which you update the weights, but nothing gets updated while doing the convolution operation. So filters or anything we don't change. That used to be the case, but when we realized why should we tell the architecture what features it should select, right? So why it should select edge, or why it should select something like object, or how it is, what color it is, and so on, right? So instead of that, we gave filters with some random values and tell it to update the weights using backpropagation. So that's how this comes into the parameters and all, right? Now again, like why should we use only one filter? We can use multiple filters also, right? So let's say this is capturing object shape and all. Something is capturing background images, like what color background is and how it is changing and all, right? Maybe another filter is capturing something like it's specific to our classification. There's a dog is there, then what is the dog in this picture and all, right? So some features of dog it's capturing, something like that. So this all things we can do, but we'll need multiple of this filters, right? So that's why this image is there. You can have as many filters you like. Okay, so this number of filters you can choose anything. So now for each filter you get some different output. For this filter you'll get different, I mean another output, not different. Generally we use similar size filter and everything. We don't change sizes of filters in between, right? So for each operation, we can choose how many filters we wanted to have. So that is what k value is. Let's say k is 5. That means we are going to use 5 filters. So in this case, it's k equal to 4. So 4 filters we are using, right? And each filter will produce another output, right? So this is all O1, O2, O3, and O4, right? There's something like this. And then what we'll do, we'll concatenate them. So this is a tensor. Again, you will get a tensor in this case. Something like, so here we started with 2D, but then we got 3D after that, right? So something like that. Now on this, if we wanted to, let's say this is my final output. Uh, let's say this is my final output, which has 4 depth. Okay, so I'll say D equal to 4, depth of 4. So what size of filter you are going to use in this? What you can use in this? I mean, anything.
Now, what is the question, sir?
So let's say my image or my output is having depth of 4. Okay. So what kind of filter I can use? Like what are the constraint my filter has? If you have depth of 4.
Sir, 1D, 2D, 3D, and 4D like filters I can use.
Yes. So 4D is, I don't think so possible, but 3D filter you can, and we are going to use 3D filter only with same depth. Okay. So let's say your size of 1 cross 1 is there, which you can 2 cross 2 or anything, right? So this 3 cross 3, these are height and width and height of the filters, which you can choose anything. 1 cross 1, 3 cross 3, 5 cross 5, 7 cross 7, anything is fine. But depth is constrained. You can't use different depth. You have to use same depth as what your input is. Okay. Because we are using that filter. So this is called 2D convolution. Like name of this is like that, because we are not going inside, right? So once you put the filter in this, you don't need to move inside, right? You just need to move from left to right and top to bottom. That's all, and all the pixels are covered in that operation. Okay, so this was parameters, and before that, sizes of anything, right? Now, now let's say if we see something like, give me a minute. So something like this, right? So this architecture for which one it is? I think it is. I think it is AlexNet, but could be different also. No worry. So what we need to check in this? Let's say you have a 32 cross 32 image, and yeah, so 32 cross 32 image is there. Now you apply 5 cross 5 filter, right? So that's what we are doing. We are applying a 5 cross 5 filter to this with how many of this? 6 of this. Okay. So how many outputs I'll get? I'll get 6 outputs, right? So you can see that's why this 1, 2, 3, 4, 5, 6 outputs are there. Per filter, I get one output, one 2D output, a matrix. Then I concatenate for each of this 6 filters. So that's why I get the finally a tensor out of it, not a matrix. Okay, I tensor means 3D matrix I'm talking about. So with side and node, right? So can you count like why what is it? Why I'm getting these outputs and all? So 32 minus what is so let's say I wanted to calculate output size. What will be the output size for 32 cross image and 5 this? Uh, 5
32
I would
minus 5
subtract.
by 1 plus 1.
Yes, so padding is
It's
0,
a
right? There is
plus.
no padding.
So 0 by 1 plus 1.
1,
1 plus 1, right? So in this case, it is
21.
28.
28.
Okay, so which is here. Okay, same thing, 28. Now comes the pooling layer. So pooling layer is something like what we do. Just pay attention that let's say my values are 1, 2, 3, 4, 5, 6, 7, 8, and 9. So these are my values in the matrix, and I use a 2 cross 2 pooling layer. Okay, so in this case, I don't need to give any weights or anything because it's not weight or something. What we are doing is we are applying some kind of mathematical equation to this. So it's like a you can consider mathematics operations we are doing. Okay, so a popular ones are one is average pooling, another is max pooling. So these two are very popular. Some also you can do, but average is more popular. Okay. So average and max are two most of the popular operations in this. So let's say I do average of this. Okay. So first I put here this 2 cross 2 filter, pooling filter. Okay. So in this case I'm talking about pooling filter. So what will be the average of these four values? So 1 plus 2 plus 4 plus 5 divided by 4, right? So that is what average is. So it's like 9, 10, 12 by 4, which is 3. Okay. So that's what you get, 3. And then you move by some stride. So again, stride and all concept remains same. The output dimension calculation, what output size you get, that remains same. Nothing changes. Just one thing changes that now will not have any weights. So weights are absent now in cooling layer. Okay. So that's why you can see these parameters are here, but there are no parameters in pooling layer. Okay, so how did this parameter came into this? Why 150 parameters here? How did 150 come?
28 into
Sir, the size is
28
5.
into 6.
28 into
28 into 6. And the
uh,
input width, whatever is input width, if it is 0, 1 means then 1.
parameters calculation.
Sir,
No,
it would
it's
be, sir, it's
5 into
5 by
5.
5 by 6.
Yeah.
This is incorrect. This is
Correct.
not
So that's for
parameter.
volume.
That is volume. Volume is output volume. What output size you get, right? So
Yeah,
that
volume
is
feature.
correct. So this is okay. This is output volume we are talking about. Output volume you can call. That is okay. For that is correct. But I'm asking about how did you get parameters?
Parameters.
How
Okay.
do you
5
calculate
into
parameters?
5 into 6.
Okay, so 5 into 5 because that is a filter size. Okay, so from here I'm taking 5 and 6 because this 6 that many filters I'm applying. Okay, if you do this, you get 150.
Yeah,
Okay,
correct.
now similar thing like here, right? So in pooling, I don't have any parameters because I didn't use any parameter. I just use some mathematics. That's all. No parameters here. But output size and all will change, right? So output dimension of this will change. So here the output dimension again by 28 minus 2 filter size I'm using plus no padding divided by stride 1 and plus 1. So in this case, I think there's a mistake that the stride should be 2. If that is the case, then only it makes it 14, like whatever the output is. Okay, then only it makes it 14. Otherwise, it's not. So I think it's a mistake. It should be 2. Okay, and so on, right? So later on you do same thing, convolution operation. Then again you do pooling layer. So after pooling, there is another concept, something called flattening. Okay, so flattening is that. So let's say you have a matrix of let's say 20 cross 30. Okay, so this is your cube. Okay, now if you flatten it, how many? What will be the output if you flatten it?
Multiply
12,000.
9,000.
12,000, right? So you just have to multiply all of them and put it in a single layer, right? So this single layer will be of size 12,000. right? So that's what flattening is, and that's what makes it actually. If you see, so initially parameters were very small, right? 150 to 2,400, but later on you can see parameters has increased drastically, like 48,000, 10,000, and so on, right? So uh, whatever you get as output, you flatten it. There is nothing you can do about flattening whatever size you get. So after flattening, that then it becomes so. Let's say you flatten it, you have 12,000 neurons in it. After flattening it, you apply a hidden layer. So some hidden layer size you can choose. Let's say you apply 10, or let's say four size of hidden layer you use, right? So hidden layer with 4 neurons. What will be the parameters in this? How many parameters will be there?
12,000
4 into
12,000
12,000.
into 4 plus 4 if bias is included.
Yes. Okay. So if bias is included, then 12,000 into 4 plus 4, right?
Yes, sir.
So yeah, so that many parameters will require, which is like 48,000. If we just ignore the bias, 48,000 parameters will be required. Even if we use very small hidden layer, right? So that's why there is a very high parameters at last, but initially parameters are very low.
Sir,
So yes,
between cooling layer and flattening, how we have to calculate the parameters? From cooling layer, you are flattening, no? So this 48, 120, how it came? Can we just work out, sir?
how did this come out?
Yeah.
Is it?
Yes, sir.
Okay. So see, so this same image. In this case, I think it is so. See here, we applied 16 of this filter, right? So this depth will be 16 because each filter will produce one. And output size, I'm assuming it's correct, which is 5 cross 5. Okay, correct.
Yes, sir.
So this is my output. So what this blue thing you are seeing is 5 cross 5 into 16. Okay, so this is the size of this, and that makes it. I think that makes it
400.
400. So, right. So 16 5 8 into 5 400. Yeah. So that is 400. Now you flatten it. Okay. So 400 is the output neuron you get. Now in 400 you are using a hidden layer of 120 with 120 neuron. That's what the FC 1 and 120 represent, right? So this is 120 in this. Okay, and this is 400. So how will you calculate parameters?
4
What will be the
plus
parameters?
48.
Yeah, so 400 into 120, right?
Okay.
That makes it 48,000. And this another 120 is coming because of bias. So this 120 are bias.
No, but bias where it is told, sir, it is not given, no?
Uh, yeah, it's not given, but they have considered it.
So, sir, bias you consider it as 1 every time?
Bias you consider it as?
1.
Yeah, so like we have, right? So per neuron there is one bias, and this is a neural network, like the normal the in week 4 or 3 we have covered, right? So same neural network, it's a normal like that. So per neuron we'll have one bias, correct?
No,
So
sir.
in
Uh,
convolution we have per filter we have one bias. Here for one neuron we have one bias.
So exam also we have to consider that 120.
It's mentioned if it is should consider biases or not consider. So if it is mentioned that do not consider bias, means all of the places you don't have to consider.
Okay.
Okay. If it's mentioned consider bias, but we'll mention that for the this like uh, neural network or whatever, like a classifier. This called classifier. You can call it. For this also, this only you can calculate the biases. Okay.
Okay, sir. Okay.
Okay. So that's what
Hey,
the
sorry, I missed it. In the bias, where were we getting that 120? We have explicitly written that somewhere.
it's not written in the slides. It's see these are slides. So slides are like professor made it, right? So he knows it. So it's not there.
The
Okay.
120 neurons, FC1 within brackets 120 are there, no? So
Yeah.
120
So
neurons.
this 120 is from here I'm taking. Yes.
Hey, 120 you said that you have 120 hidden layers. Hey, 120 neurons.
120 neurons in my hidden layer. So hidden layer is there with 120 neurons.
And we assume bias to be 1 then?
Yeah, of course, right? So per neuron there is one bias always. Like if you consider bias in a neural network, and hidden layer has one bias per neuron, right? Always.
Okay.
Always means if it is if you consider it.
Now value of the bias is not one. Number of biases is one per neuron.
Yes. Yeah, number of biases, not values. Values will be anything. It's a parameter. Number of biases will be 120. So
Okay.
as many neurons are there. Okay. Fine.
Yes, sir.
So now, okay. So now if you are interested, like, see, this is a max pooling operation they are doing, right? So for this filter you put here, so stride equal to 2 they are doing, right? So what is the maximum value? You take out that and you write it. Then you move by stride 2. So stride 2 would be this, right? And then what are maximum value, which is 4. Again, like you move here, and what are maximum value, which is 7. They put it, and then finally, like the last move you make, and maximum value, which is 5, you write it. So this is a max pool operation. So right, so average pooling, if it was average pooling, I would have added all 4 of element and divided by 4, because that many are there. If it's a 3x3 filter, then you have to do similar thing, right? So 3x3 means, let's say if it's a 3x3, then I'll put my filter like this, and whatever maximum value out of this, if it's a max pool. If it's average pool, I take all 9 elements, add them, divide by 9. That's what averaging is. So this remains similar, like the concept wise. Sizes increase, degrees, that can be there. Okay. Okay, so that's what the pooling is. Now, okay, so some architectures will be there here and there, that which they've used, like similar thing. See, now for LeanNet 5, they are doing something. You don't need to remember exact architecture of anything, like what is LeanNet architecture, what is LXNet architecture is. That is fine. Like you don't need to remember it. Okay. Now some other Google Net will be there. Some other architectures will be there in that. Okay. Now, so something like back propagation of neural network is there. So in this case, if we have a filter, let's say this filter is there, and I applied it here, right? So let's say W multiplied here X, Y, and Z. I wanted to update the filter, but that is not simpler, right? Now you can see that um, I think they made a mistake here. It should be W, X, Y, and Z. Okay. So you can see that my W, if I, let's say if I move this filter across it, then my W would have, if stride equal to 1. Okay, so stride equal to 1. My W would have multiplied here also, right? Because I would have moved by 1 step. Then I would have moved down side 1, and here also, right? So there's 4 places where W, this one parameter, is contributing, right? So now I'm doing parameter sharing. So that's why this 4 places where it's moving. Similarly, X will be doing same thing, and Y and Z also will be doing same thing, right? So now if I wanted to do this a back propagation, okay, so what will be the uh, what I need to consider in back propagation? Gradients, how my gradients will be affected by this. So in this case, your chain rule will be little different, right? Your chain rule is, so like first equation was some WB, then something, right? So whatever this X, C, and so on. My second equation will be WC, and third will be WE, and WF, right? So there's 4 places where this W is contributing. And if I take, let's say, derivative of anything with respect to anything, right? So just say some value is there with respect to W. So in this case, like the first will produce B as a derivative of that. In this case, C, E, and F, right? So something like that will be there. So that's what like you can do. For that, I have taken, so in my in weekend live session I explained it, but I'll again go through it. Like what is it? So I think I have. Yeah, so I have this. Okay, so let's say if you have um maybe before that I would like to show you something. Okay, so these are the slides. So let's say this is my input, this is my filter. I don't think I can write it here, but yeah, it is just I can maybe use. Okay. Wait, wait a minute. Compress CM or something like that. I think I have annotated this, but it's fine. So this is my input and my filter, right? Now, so this is my operation, right? So I do convolution operation, I get O11, O12, and so on, right? And similarly, yeah. So this is what inputs say X11 into F1 and so on, right? So now, if you see this 4 equations where it has contributed, right? So O11 got this 4 X11 with F11 multiplication and so on, right? So this is how you get this convolution operation, F and F, and you get O as output. Now, let's say you wanted to do this uh, gradient calculation. So till O, some O before O, something will be there, right? So some, let's say before convolution, pooling layer would be there, or let's say some the neural network is there or something like that, right? So this gradient you will be able to calculate because the gradients for initial layers like let's say initial layer was this softmax. Okay, so last layer. So last layer is softmax. You from this you produce y hat and which you use for loss. Let's say loss is cross entropy. Okay, and then you have some hidden layer. So this is my first or last hidden layer or something like that. Now, if I ask you what is loss with respect to the whatever my input going to the last layer, AL, let's say AL, right? So softmax of my AL was y hat or HL. You can call anything. So but this is a pre-activation value, right? So W, some weights will be there. W and AL is W into whatever my H1 is. Okay. Something like that. So here if I ask you what is gradient with respect to AL, this part you know. So this part is in back propagation of the neural network, right? So you know that it is y hat minus y, or vector will get out of it. So just consider that let's say that's what it is. Like the initial layers, you did some back propagation, you get that. So dl by do, you got that. Now O is the one where you used convolution operation, right? So convolution operation is what happened here, and how will you do gradient calculation for this part? So this part you can if I go like and explain everything, it's like you expand it, then you can see there is a like O11, then O11 with respect to F11, then O12, in that also I'm going O21 and O22, right? So there's four places as I was talking about. Right? So there's here, and there, right? So these four places F11 contributed. So that's why I'm considering all four of this, or you can see this part of the equation, right? So these four places where F11 contributed. So that's what I'm writing as a gradient of each component, and then I'm able to calculate that. Okay. So if you wanted to do that, what you will get? What you will get as a output in this case? For example, uh, yeah. So just now so for this part, right? What will be the output of this O11 with respect to F11? You want the equations? Let's say equations are this, right? So I'm asking what is O11 with F11? What will be the output in this case? This is the equation.
X11.
X11, right? So this will become X11. Similarly, what will be, let's say, O21 with respect to F11? What will be that?
X21.
X21, right? So this one, correct? So this part is very straightforward. Like whatever the equations you wrote, you take a derivative with respect to the filter, and in this case you will get whatever is in the multiplication. So it's a straightforward derivation. So if you do that, and you write all of them, right? So in this way, so what we exactly trying to do in this case is, give me a minute. Sorry. No, not this part. Uh, okay. So what we are trying to do is we are actually doing a convolution operation. If you wanted to summarize it, then how will I be able to do it? Like you don't want to remember the formula. So if this operation you are doing dl by f11, what you can do, whatever your input was, right? So this was my input. Whatever my previous this derivative was, right? So dl by o11, whatever it was, I will write that, and similarly O12 and O21, O22, something like that, right? So all four elements I can, and I have to do a convolution in between them. So now this becomes a filter. Whatever this initial things were in my back propagation, I take them as a filter and do the convolution operation, and whatever output I get, that's what the final result is. Okay, so if you wanted to do derivative of this uh, of the loss with respect to filter, that's what you have to do. You just have to compute initial till O11. So till O you have to do, and then you have to write them and do the convolution operation. Okay, so similar thing you will do with respect to the x also you can do. So where x will be required when you have a convolution in between. So for example, this image, a convolution you did, now some pooling operation you did, and then again you are doing a convolution operation. So in this case only you'll require, when you wanted to do a gradient backtracking in this, or you wanted to go back in this, that's where you will require whatever your output is and gradient with respect to x. Then only you will require. Otherwise, you will not require. Okay. So that also you can do, and to come to the conclusion, what you have to do is you have to. Okay. So in this case, what you have to do is you have to take the filter, right? So just remember that f and x. So filter and x, right? So that's what produce O. Now, if I ask you what is O with respect to f, you will say x, right? And if I ask you what is output and derivative with respect to x, you will say f, right? So that's what derivatives are if you have a multiplication. So similarly, with respect to x, if I ask, you have to use a filter as the thing. You have to rotate it by 180 degree. Okay, so this is 90. So this is my filter. You rotate by 90, and this is rotation by 180 degree. Okay, so whatever these values are coming, you can see that's what they have written here, and you rotate the filter by 180 degree, and then you take something called full convolution. Okay, so full convolution operation is something like you put a filter uh, and do it. So don't worry. The example of this is much more intuitive, or maybe easier to understand. Not this is a week 8. I think it was this one. So if you are able to understand, so let's say my architecture is something like this. I have my input, and I apply a value. I apply convolution operation. Then on convolution, I can apply some form of activation function. So this convolution you can kind of think as a pre-activation. Okay. Then on pre-activation values, I can apply ReLU, sigmoid, or any LU, right? So whatever activations you might have studied, you can apply that. That's what you can do. Then you apply some form of pooling operation, and then you do flattening of that, right? So flattening you can do. So after pooling, maybe if you do flattening, again you can have hidden layers and so on. But I'm not making it complicated for this example. Then what you do is you apply a softmax. Right? So that's what, let's say, architecture is, right? So give it little bit of time and imagine this architecture in your head, like what is this, right? So image is there, then you apply convolution. Uh, Give it some time. Imagine this, that this what you are doing. Okay. Okay. So now this is my image, and let's say this is my filter that I wanted to apply to that. Okay. So as of now, one filter only. You can have multiple filters, but we don't need as of now. It's a simple example of that. Slide one, no padding, no bias. Where bias you can actually not zero, but to like exclude the bias. That's what I wanted to represent, but like something. Okay. So if you do that, what is the output size? In this case, 4 cross 4. Okay. So you can do like 6 minus 3 plus no padding. Stride was 1 and plus 1. Right? So 6 minus 3 is 3 plus 1 equal to 4. That's why I'm getting 4 cross 4 output size. And I'm doing convolution. If you do the convolution operation, so this is what convolution is, right? You multiply each element and then sum it. So that's why minus 3, then this all values will get. And you can see this is the 4 cross 4 output you are getting, right? Now, on top of that, I'm asking to apply some activation. So let's say ReLU is what applied. So how ReLU works? Any negative value, you make it 0. And if it's positive, you let it be, whatever it is, right? So that's what ReLU is. Like x, if greater x is greater than 0, or 0 if x is less than 0, right? So something like that is uh, yeah. So anyway, here you can have it. So something like that is a value.
0x, right? Okay, it's written, sir.
Yeah. Okay, so that's what ReLU is, and that's what we are doing. So minus 3 becomes 0, and this all becomes 0 and 0, right? So that's what we did. Now you apply, it's a pooling operation on that. So that's what in the architecture you do. The pooling operation, let's say you do max pooling, right? So max pooling is very easy. What you do is you with stride 2, so you put here whatever maximum value you take out, and then move by 2, and so on, right? So just in this case, we got this 2 values. Now see here, this is a case of clash, right? So now, clash.
First time forgetting or something, like when we are taking slide 2, we are taking a 2x2 filter, right?
2x2 filter. Yeah. So filter size is 2x2. That is here. Stride is 2. Okay. Yeah. Filter size is mentioned differently, and stride is mentioned differently. Like they should both be mentioned. So if you have this pooling size, let's say 2 × 2, your max value is 1, right? So this is also maximum value, and this is also maximum value. Both are possible maximum values, but you take out 1, right? So how do we decide which one to take? Like that is not something we can do, but uh, how programs were written, just take the first one, whichever comes first. That means whichever comes leftmost first and topmost first, right? So topmost, leftmost, you take that. As of now, you consider that only. Okay, whatever left and topmost, you take that. Okay, and go with it. So that's what we'll do. So that's why I have taken this two as a this 4 values as a maximum of this 2 × 2, and you get the final output as this. Okay.
What did you say? Like take the topmost one. I missed that.
So you apply a max pooling on this, right? That's so this was your filter. This now you wanted to find what is maximum value in this. Now this both of them have equal value and they both are maximum, right? So how do you decide which maximum value to take? So in this case, you take the leftmost and topmost, whichever is- whichever comes first in this
Okay.
order.
Okay. Thank you.
Okay. So that's why this one I'm taking, and similarly, that's why I'm taking this two and not this two. Okay. Similarly, I take this and this, right? So that's what I'm doing. And finally, after pooling layer, this is my output. Now, same thing. What I need to do, I need to do flattening of this. So I do flattening of that. Right. So this is my flattened thing 1 2 1 1. How you take this row and then next row. Okay, something like that. That's what flattening is. And now let's say this some weights are there, right? So let's say my final flattened layer was this. I have 3 classes. So that's why how many neurons required in the output layer? 3, right? 3 neurons required for output layer. This is my output layer. And how many weights will be there in this for output layer?
12.
12, right? 4 × 3, 12, right? So that's what this matrix is. So you can see 4, uh, it's 3 × 4, right? So that's how I got it, right? And now you do that, multiply, and you get this as a pre-activation. Now you apply softmax over it. So you apply softmax and you get some probabilities, and finally you decide that uh, predict class 2 with whatever. So this is just a don't worry about this. So this is the prediction, right? That 0.16 or whichever is the highest, right? So highest is the one this one. Uh, 0.844. So loss is this much. This is your loss. Now you wanted to reduce the loss. That's what the idea is. Correct? You take softmax, you compute loss, and you wanted to reduce the loss. So for that, you'll use back propagation. So now we'll see what is back propagation. You have loss, you had softmax before that, you done flattening of this, right? So you call it fully connected layer. That's why this FC is fully connected. So, and here we are doing flattening, then pooling, then ReLU, then convolution, right? So that's what, if you wanted to compute this DL by DF, right? So what we saw in the previous slide, we need first with respect to output, some output, right? So here somewhere output was there. And then with respect to output, I can do with X also. And then with respect to like similarly, if with respect to X was asked, then I have to do, sorry, here it should be F and here it's X, right? So that's why these two things are separately, right? Now in this case, like you need to compute DL by O. So that's what, how will you do that? So this is the chain rule of that. Okay, just give a little bit time and give it a give it a thought, like why this is the chain rule I've written. Is there any mistake in this, or is there anything wrong with this? Is it correct? Can you write this chain rule by yourself? Okay. So any of this like terminology is difficult. Can you write this chain rule? If you can write this chain rule, then you can do the derivation. Like you can definitely be able to write all this value. Right, each of this value, I I can certainly say that you will be able to find it. Right now, multiplication is of course you will be able to do it, but this writing this chain rule is the part. It's always a part, right? Even in the normal neural network also. Here in CNN also, you need to write this chain rule. Then otherwise the rest of the things are easier because you know how to take derivative with respect to ReLU, how pooling layer you can do, and whatever this intermediate values and all, right? So other things you can do. Fine. Okay. Okay. So let's see how we can do. So we'll see first we have this loss, and then how I can take derivative of loss with respect to the actually I need to do with yeah, so dl by, actually I wrote z, but it should be al. Okay, so this is al is pre-activation of softmax, right? So my softmax, or let's say my, sorry, so this is my flattened layer. I use 3 of this and then use that for computing y hat. What I'm talking about is al, right? So last layer, then I got HL, or you can call y hat also. Both the things are same. So HL and y hat are same. Okay. So that's what I'm doing. If I do that, I get y hat minus y, right? So this is I know from the neural network session lecture, right? Now I need to okay. So I have this thing, okay, and I have this flattened layer in that. Okay, so what will you do for that? What will you do for flattened layer? Uh, so let's say I have this flattened layer. Okay, now uh, now before that it was a matrix, right? Then I flattened it. So what will I do is I do nothing, but I just do it deflattening it, right? So I whatever my shape is, I deflatten it. Okay, so that's what we will do. We will have this as the output. This is my uh, yeah. Actually, this weights are the one which are coming in between, right? So I'm updating this weights as of now. For this weights, you have to multiply your loss uh, with the output in x, right? So h naught. This is h naught transpose or something like that you have done, or whatever h t minus one transpose of that. So that's why this is coming, and finally this, right? So yeah, okay. Now okay, so our architecture will go back to the architecture. Let's say you have loss, you apply softmax, you have fully connected layer. Now for fully connected layer to pooling layer, what you have to do, you have some flattened layer, right? Now flattened layer, you transform it back to the shape it was, right? So it was a matrix, and you make it as matrix. That's all. So you took each row wise, and then you wrote it here, right? So again, you'll put back similar matrix. Just remember, you will get similar vector. Okay, similar vector you will get. You just have to make it in similar matrix. Okay, so don't get confused. Like what? How will I change it? So if you are taken row wise, or whatever, like so do that only. But you revert it back to the original shape, right? So that's what we'll do. So we got this, and we will like kind of change it to whatever way it was. Okay, so take first two, and then you convert it. Okay, now in pooling, right? So pooling, what we did, we had this matrix, and from somewhere we took the value, right? So let's say it's here, somewhere here, and something like that. So you create similar matrix, and from wherever you took the value, you put back that gradients over there, right? So You took it from somewhere, you put it back to that. That's what the gradient of pooling will look like. So back propagation of pooling will look like. You put it back to the original size matrix which you have. Right now you apply ReLU. So what is the derivative of ReLU? Uh, Nothing but wherever the negative values were, you made it zero, right? So I think that is already being considered because the negative values in my ReLU were uh, here, there, and there, right? So this all places, I just need to make sure that this values uh, this value does get like zero in backward also, right? Because in forward pass they never contributed anything. So in back pass also, I'll make sure that they don't contribute anything. So that's what I'll do. Where was I? Here, right? So this ReLU operation, this mask you will get. So this mask means like wherever it was greater than z, I wrote one. If it's less than zero, I put it zero, right? Because they never contributed to the uh, uh, in forward pass. So that's what we'll do. And if anywhere it was value, I would have certainly made it zero, but it's already zero, so I don't need to do anything in that cases, right? Now the convolution filter part comes in. So with filter, what we do, we take convolution of filter, convolution of image, this part. No, not this. Yeah, so this part will do convolution of this, right? So convolution of input and whatever loss we have just now computed, right? So input will take, this was my input, correct? And this was my gradient just now I computed dl by do. This was my d, this was my whatever my input was, right? So I take the convolution operation and I get this as output. Okay, fine. Similarly here, what I'll do, I'll take rotation of 180-degree. That's what I've done it. And I'll do full convolution. So full convolution means you add some padding to it. So for example, uh, you can see that this is a full padding, right? So I've added padding. Now how will you decide what padding size you have to use? Zero padding on all sides, which is k minus 1. Like uh, k is the size of filter. Okay, so let's say your filter was 3 cross 3. You take 3 minus 1, 2. Right, so 2 padding you'll do around it, all around it, and then you take full convolution of that. Okay, so if you take full convolution, you'll get this as output. So spend some time on understanding this. I already shared this in the group. In last lecture, I did cover it, but still I am don't know if it's understandable. It's a little hard,
Can you,
but still.
can you again give the URL for this, sir? Can you share it here?
I have done it, right? So it's there in the group. You can check. It's there in the. But I'll share it after the session. Okay. If you like. Okay. Okay. So this is on CNN. If you have any questions on CNN, you can ask. I don't know if there is anything I can. Yeah, there is anything remains in CNN. Almost.
Sir, one question was there, sir. Updated value of W. How you can find, sir?
So how means which W? Where W?
In the filter, it was a 2 cross 2 filter we are using. No? So, in one question they have asked updated sum of weights.
Update the weights. Yeah, so filters are weights, right? So filter has all the weights. That's what we are doing. So this DL by DF.
So we have
That's
to
what
find out all the weights and then give a sum, or how it is that?
that could be depends on the question. Can you share the question? Then only I can say.
Yes, sir, we can do that, sir.
Yeah.
It was week 8 graded assignment last question, I feel.
Okay, week 8.
In which it was asking like the updated value of W.
Week 8 graded assignment. Last question. Enter the updated value of WK, and W1 was uh, A1. Okay, so now go back to question, compute the gradient, update the W1 and W2. So they have mentioned that W1 and W2 uh, uh, were the part from the filter, right? So filter is in this case it's a just a vector, and first element is W1 and second element is W2. Now they are asking with respect to W1. Okay. Okay. So see, give me a minute. I'll show you the.
Can we work out this solution once? That would be better.
Okay. See, the question is first. Let's see the question. The question was that 1 minus 1, 2, 2 minus 2, all zeros, then 1 minus 1, 2, and minus 2. Okay, so this is my image or input. My filter was something like my 0.6 and minus 0.2. Okay, now again, t cross 4, the truth, the y is 0.1. And suppose we use 1 plus 2 with stride of 2. So they are using stride of 2, and no padding was given. To though you can answer many question, something like that. Compute. Okay, so first they are asking what is convolution between x and k, and store the output in matrix A1. Okay, so A1 is x convolution with k. Okay, now I can do that, but it will take some time. But I think so. We have given solution. I'll take a little help. So A1 is coming out to be 0.8, 1.6, 0.8, and 1.6. Right. So this is what my A1 is. Convolution you do. You put here, then there. Similarly here. No, there you can't. Sorry.
The stride is 2, so it
Stride
would
is
just
2.
skip
So
that
you have to
middle row.
move
Yeah.
here, right? So these four things you apply your filter, and then you get A1 as output, right? Now, mm, now, okay, what is the next thing they are asking? They are asking something like okay, sum of A1. Fine, you can find A1. So sum of A1 is something you can do. Now A1 is passing through sigmoid, right? So that's what we did ReLU, but they are saying that passing through sigmoid, right? So let's say H1 is sigmoid of A1. You apply sigmoid over this, and you get output as 0.69, 0.83, 0.69, 0.83. Okay, same thing. So in this case, you get H1. Fine. Now they are saying that do a flattening of this, right? So whatever you can call flatten layer, right? So A2 or anything. In this case, you can write 0.69, 0.83, 83. Right? So this is flattening of this.
Sir, how are you calculating the sigma value so fast?
It is there in graded assignment solution.
Okay, you're discussing that. Right?
Yeah. Okay. Now flattening we have done. Now ask this: what is flattening? And then okay, flatten the H1 to feed as input to sigmoid neuron as follows. So they are they're telling me that what you should do is you you should sum all of this flattened values and then pass it to the sigmoid, right? So sum of all of this and then pass it, right? So whatever this values I did, so over the time I'm doing it, and that's what is y hat also. So sigmoid of sum of this is, so first summation is, let's see what is the summation in this. Yeah. So this is like summation is 0. Sorry, it's 3.04. Okay, and the sigmoid of A2 is y hat, and that is coming out to be 0.95. Right. So this is what my y hat looks like. Now they're asking what is mean squared error. So y hat minus y and whole square of that. So what we need to do in this case? We take 0.95 and our y was given initially, which was 0.1. Okay, you take whole square 1/2 whatever, and then you get output as 0.36. Okay, so this is what loss is. Now what is the gradient? Do back propagation to compute gradient of and update the weights W1 and W2, right? So W1 and W2 here is this filters, right? This filters thing. So what we did as of now, let's see. See, we had this image, we applied a convolution, we applied a sigmoid, okay, we applied a sigmoid, then we flattened it. So flattened it. Then what I did, I actually took summation and then right. So now depends like what kind of changes you make. Depends on that, you have to do the gradient calculation differently, right? Now the flattened layer is there. You sum it, so sum of that, and then you take sigmoid again, and then from sigmoid you call it as y hat, and then the y hat is used for loss, right? So this is my cycle. Now they're asking how will I update this, right? So from DL to the convolution before the sigmoid, you have to calculate that, right? So that's a DL by, in this case, it's a mean squared error. So you have to, it is going to be something like this, right? 1/2 into 2 y hat minus y, correct? So cancel this, you get this as a loss with respect to y hat. Now y hat is what? It's a sigmoid, right? So sigmoid derivation is, what is sigmoid derivation?
1 into 1 minus sigmoid.
Yeah, right. So sigmoid of A2. So I'm calling A2 as whatever going inside this, right? So this is what you get y with respect to or yeah, y with respect to A2 actually. Okay. Now what we are doing before that, I'm taking sum of this. Okay, so summation A2, summation of that is A2, and before that is fully connected layer. So I don't think so I need to do anything. And okay, so here the summation. So just wait a minute. I'll write all this, and so y hat minus y will be 0. What was that? 5 minus 0.1. Y hat minus y I'm calculating. So this is 0.85. Okay. Now the sigmoid part has value of, so the sigmoid, right? So y hat with respect to A2 is 0.95 into 1 minus 0.95. So this value is 0.047 as of now. Okay. So finally, like DL by A2 is coming out to be 0.04. Okay. So multiplying this and this part. Okay. So this two thing, if I multiply, I get this as output. Now what I have to do is, so I took sum before that. So sum is addition, and okay. So the summation, let's say I have four things, right? X1, X2, X3 plus X4. So this four things I sum up, and I ask you to take, let's say, whatever, like derivative with respect to X1. What is going to be the derivative of X1? 1, right? Just 1. This will be 0, 0, 0, 1. Correct?
Yes, sir.
Similarly with X2 also, if I ask you, then also 1. Again 1. Right? So all of them will be 1. So there is nothing I have to change it here. Right? So summation. So dl by, let's say, summation, the summation part, if I ask you, then you have to multiply this part 0.04 into 1. Right? So for all the values, you will get 1 only. Right? Nothing changes. Now, what we are doing, we have flattened it. So we'll deflatten it. Right? So this deflattening part is something we have to do here. So how will I do that? I'll write it as of now 0.04, 0.04, something like this. Okay, so this is this should be the deflattening part. Now, what is it? H1 by A1. Again, sigmoid, right? So we have again sigmoid here. So this is this sigmoid. Again, like sigmoid into 1 minus sigmoid. So what was the sigmoid value there?
0.69.
Fully connected. Wait, so fully connected layer was oh no, it was different, right? It was like this, yeah, like this. Now you take whatever, right? So 0.69 into 1 minus 0.69 and something like that. So 1 minus 0.69 and multiply it, and that's so on. Right? So I think that is also calculated here. Yeah, I'll write that directly. That is so that is coming out to be 0.21, 0.14, 0.14, 0.21. Okay, so that is what sigmoid is. Now, sigmoid part is done. Now coming the convolution part. Okay, so just bear with me. What we have done is we needed with respect to, let's say, filter, right? So because filter is containing W1 and W2. So now first we should do till whatever output was till convolution, right? So input convolution, and here till here we have reached there. So D, that's what DL by DO is. Now DL by DO by F, right? So that's what we have to do. So this part is what we have to do, which is just convolution operation between the input and this thing, right? So that's what we'll do. But here see this part. What I got is I got this 0.04. So this matrix and this matrix, I have to multiply them. Okay. Does it make sense? This matrix and this matrix I have to multiply, but it's not matrix multiplication. It's like a element wise 0.4 and something.
So are you like taking the 0.04 out because it is anyway one only, right? Because it's like or something like. Is it
Yes.
like Adam-odd multiplication?
Yeah, Adamant product, right? So Adamant product like that you have to do.
Okay.
For sum, then summation was flattened. So we deflattened it. The deflattened one, uh, flattened one, then just give a minute. So this was my thing. This was the case. I flattened it, then summed it. See x1, x2, x3, x4, x4, and summation is plus x4. Okay. Now with sum, whatever my sum is with respect to this flattened layer, it's always one, right? So uh, one, one, and one, something like that. Because uh, yeah, now I will deflatten this one, one, one. So that's why I got this. Yeah, till here it's fine, but before that, uh, before that, it's a different thing I do. Before, okay, flattening, then I applied. Okay, so this flattened was sigmoid. So for sigmoid, I do 1 into, yeah, that's correct, right? So that's what we'll do Adamant product because it's a sigmoid. Okay, so this x1, h2, x4 are sigmoids, right? So for sigmoids, I mean, this will be transformed into 1 minus whatever it is, right? So that's why it is again coming out to be as matrix only, and that's what this Hadamard product I'm talking about. So here I considered 1 only, uh, but this were not ones. I mean, this calculation I made it. Don't worry about that. What you have to do, you have to multiply this with this as a Hadamard product. Okay, so you multiply element wise each of them, and you get something as output. Okay, so whatever output you get, that looks like 21 into 0.04. What is that? That is okay. That is 0.0084 and 0.0056. So I think for this kind of problem, they must have used calculator or something. You don't have to do manually, or you can write code also. Like while doing GA you can write, but in quiz you can't. Okay, so now see last part remains. What you have to do, you have to take input, whatever input was. Their input was 1 minus 1, 2 minus 2, 0, 0, 0, 0. Similar thing again. And then you do convolution operation on that, right? So of this matrix, you can write here and then do the convolution operation. So convolution is again like uh, uh, with stride 2, right? So you use stride 2, so you have to use the stride 2 only. There is one mistake in this. Actually, you don't do stride 2 or something. Actually, it's a little different. I think in solution it's given incorrect. What you actually do is you apply, now how will I call it? You you expand it. You don't do as it is. You expand it. For example, you add a 0 in between or something like that. Right? So this expansion should be done. So if it's just right equal to 2, then it's not that straightforward. It's a little different. So I think what they have done looks incorrect to me. I'll check. So in this case, actually, so strides, if strides is higher than 1, you can't do the conversion operation which I showed, right? So this operation is that was it for here, right? So this operation is only valid if your stride is 1. Okay, so this operation is only valid if stride is 1. If stride is 2 or higher than that, then it's a different case. Maybe you can look at somewhere else, but it's not needed for the. So for stride 1, you have to do this. Okay, so just assume that stride was 1, and I will do that. Okay. Uh, does it make sense? Okay. Maybe look at after the class. You can pay like you can maybe give some time to it after it equals also for stride equal to 2 not needed. Not needed. Stride equal to 1 is this formula. Just remember for stride equal to 1 only this formula holds. Otherwise you have to make some changes in input x. Other similar thing we are going to do, but we are not going to use similar x. We'll do some expansion into that diluted x or something like that it's called, and then only we do it, right? So we apply some padding in between like somewhere. Okay. uh, uh, I don't recall exactly how it is, but uh, for this you do that. Okay. So that's what there for CNN. Yeah, if you have any question you can ask, or we can maybe move to other weeks. We have consumed a lot of time on CNN. Okay. Okay, so let's move to week 5. Some optimizers we can cover that. Week 5. Okay, so this no NAC. Okay, RMS prof and net credit is actually there. NAC. Okay, so this is in week 4 only. You don't have to go to that. So here week 5 is there, right? So now what is the thing we needed, or what where we reached before this is we had some the normal gradient descent, right? So where weights are there, you you update weights. So for the t plus 1 from t, some learning rate you use, and then you use gradient of loss with respect to the weight. Right? So whatever weight is, you do. This is a normal gradient descent. Now, what possibilities or how do you optimize this equation? Either see only two options are there. Either you do something with this, okay, or you do something with this, right? So change either of that. Either learning rate, you can have some adaptive learning rates or something like that, or you can have some adaptive gradients. I mean, some history of gradients you can use if it is useful or not, right? So these two things are there. I think so. Adaptive learning, or possibilities that you have some history of gradients, right? So maybe use something like use history of uh, gradient. So earlier we saw in momentum based. So one we saw momentum based, right? So in that we use some form of history to have a momentum, right? So we stored or we um, combined or we what I call that we add up, right? So we add up the history and then we use it for momentum, right? So that's what momentum did. We use some form of history, and then in NAC we just did it better, right? Something like we don't have to have much more oscillations. So to reduce the oscillations, we did similar thing, but uh, uh, we did in parts, right? So that's what NAC is. Now, what we are exploring what we can do with the learning rates. Right, so that's where comes the first our first optimizer adder rate. adaptive gradients or something, right? So there we will not do anything with the derivative, right? So this derivative part will not do much with it. We'll use some form of learning rate, which is different from previous thing, right? So now we're focusing on learning rates. So some learning rate. What we are doing is let's say uh, my gradients are there, right? So okay. So let's say my one of my steep curve is there. So a curve which is steep. Another is shallow. Okay. So what kind of learning rate you require in these two cases? What kind of learning rate is required?
Steep should be smaller and shallow we need like bigger steps.
Okay, so it's little bit like or bigger, right? So smaller and bigger learning rate, right? So I'm talking about theta here, right? So that's what we require. So how can we achieve that? What? So let's say if I was moving let's say if I was moving here in a steep direction, I was here, and my gradients I'm accumulating, right? So my accumulation of gradient is something like this. You can say I'm squaring it and adding it up. Okay, so this is continuously increasing, right? So what part I'm increasing it? The VT part. Okay, this equation is increasing. Now let's say I reached a shallow point. Okay, but my VT is still high, right? So it's very huge. I've reached here. So my learning rate was, let's say, it's a 3 or something initially. I'm dividing it by that very huge number, right? So whatever my huge number was, and what it ultimately is doing, it is making it smaller, right? But this value is going down. If I reach to a, sh- a shallow point, right? So what my point is that this graders were not the best, but that's what they tried, right? So they tried it, and the issue was that once the gradient or once the learning rate crashes down, like once the learning rate goes down, you can't increase it. So there is no way it will increase, right? So we needed a bigger and shallow things, and we needed smaller and steep places, but we couldn't able to do it. So if it is steep and continuously steep, so for example, this is there. Let's say here learning rate was we started with 3, maybe like here if you reach your learning rate might be very small, right? So for steep things, it is good. Like after certain steep movements, like steps, you might reduce your learning rate, and so on, right? But once the learning rate goes down, it will never go up, right? So that's what the drawback of this. But but that's what they tried, right? So they wanted to have uh, this was the idea, but they couldn't able to implement it. But at Grade, what they did is they were able to control the learning rate in some form in steep regions. So at least in steep regions, we were able to control the gradients. Okay, and you can see that. Uh, okay, yeah. So here one concept I forgot to mention that something called sparse and dense feature is there, right? So dense feature. So sparse means that most of the values are 0. Okay. And dense means values are not 0, some value like 1, 1.2, 0.8, something like so some values are these are dense features. So wherever this sparse features are there, where gradients are not updating, right? So my gradient is itself 0, right? So in this case, what's happening? The learning rate is not reducing, right? So for those cases, it worked. Like the learning rate was not dropping down for the sparse features. Okay, for dense feature, it is crashing it. Okay, so for the uh, so if x is sparse, then not b yeah bt. So okay, here the okay, so we'll take it for uh, w, which is sparse, right? So for sparse feature, gradient is 0 for most of the time, and that's why this learning rate is not decaying, right? So the learning rate is not decaying, but let's say my b is there. So b is the parameter which is not sparse, right? So it is a dense feature. So for that, what is happening? Uh, the gradient of BT will not be zero for most of the time, and that's why so the final conclusion is that it is decaying rapidly, right? Something like that. So uh, for gradient of del W T is here, and uh, uh, yeah, so you can see in all the cases VT was constantly increasing, right? And learning rate for this case is rapidly reduced. Within case, it remained almost linear, right? It didn't change much. Like it remains constant almost all the time, and that's why the curve is coming smooth, or the decaying is happening in both the cases, right? So that's what we wanted. The issue was that uh, let's say my uh, optimum or the minimum value lies here, right? From here, if I start, I should go like this and reach there, right? So this is the best path, best route to it. But that's how it doesn't happen. So if you use the normal gradient descent, what happens is we move like this or like something like that, and so on, right? Uh, so what happens is if your feature is dense, so first it goes uh, for this learning rate decays, or learning rate, not learning rate, but weights reduces much faster, and then it moves in that direction, right? So for sparse feature, weight updation doesn't happen. Weight updation, like so for updation doesn't happen for sparse feature. For dense, it happens continuously for all the time step. It happens, and that's why in one direction it goes, then it starts crashing in another direction, right? So that's what we wanted to not to happen. So what we did is for dense feature, we had this adagrad thing component. So wherever dense feature is there, for that it will not let it move faster, and for the sparse feature, it will not reduce the learning rate, right? So that was the concept which they used, and that's why this ADA grade comes into picture. Now we'll have some problems like VT is always increasing and so on. So for that purpose, what we did next is we use some, like, we'll not use all VT. We'll use some portion of VT, right? This is called exponential moving average, right? So that's what we are doing, exponential weight average or something like that. So we'll use beta of that and 1 minus beta of this. And so if you do that, see what changes are now. Therefore, take a slowly compared to at aggregate for B. Uh, yeah, so continuously, like, so once it is reduced, now nothing you can do, right? But in this case, it is still decaying, but decaying slow, right? For B, that's what this proof actually shows, that's what we'll do. You don't need to go in that much into it, but I'm just explaining it for why this is coming into in there, right? Now, both of them have still similar issue, I guess, that Gada get very aggressively, then something like that. So what you can do next is probably okay. So let's see what are the drawbacks of this. So sensitive to initial learning rate, initial condition of the parameters and corresponding gradients, both for RMS and data grade, makes a lot of difference, right? If initial gradients are large, the learning rates will be low for the remainder of the training in data grade. If initial gradients are large, so initial gradients are large, but that means like the VT will be high, right? So and that's what makes learning rate smaller. So that's why, like, the learning will not happen. So in gentle curve is encountered, no way to so no way to increase the learning rate in data grade, right? So there is no way to do that. Even in RMS prop also, I don't think so. It is something we can do. We can't increase the, or we can't Uh, Probably it will reduce because we are taking beta of that, and once like exponential of this will reduce. So at least denominator will be little bit lesser once we pass somewhere, right? So some form of uh, controlling we are doing, but not much, right? So that's where like comes the ADA delta. So what they do is they use two of this UT and VT. Now one is yeah, UT and VT, right? So UT and VT. So which are one time step ahead, like VT is one time step ahead and UT is one time step lagging behind it, right? So like UT is let's say here and VT is kind of here, something like that. And then you use a ratio of that to control it. Okay. So similar thing here in this case, we have some control over the learning rate, and if it's a steep curve, then you might have uh, different results. And when it is shallow curve, you have if the gradient remains low for subsequent, right, then the learning rate grows rapidly. So, yeah. Uh, Yeah. So see this part that if VT grows, then UT will grow. Same thing, right? So it is just a one time step behind it. This UT is one time step behind the VT, right? So there is nothing you can. Uh, so there is nothing we can do in this. Like we have this two things. One is going behind this. So if let's say gentle curve, right? So this gentle curve comes in, then both of them will have smaller values. So ratio of smaller values again a higher value, right? It's a 0.2 divided by 0.3. What is it? 2 by 3, right? It's a bigger value. So 2 by 3 is 0.66, right? Which is higher than both of them. Correct. So that's what we are doing. If it's a gentle curve, you'll get a higher value. If it's a steeper curve, then both the values are going to be higher. So in this case, we'll have like let's say 4 by 5 or something, right? So in this case, we'll have smaller value, like it's 0.8 or something, which is at least lower than the gradient itself. Correct. So these things we can use to have like smaller gradient or smaller learning rate in steeper curve and higher learning rate in gentle curves, right? So that's what this ratio will help you in doing that. So that's what error delta rate. Now, see this equation you don't have to remember. We'll provide that. So at least what is the idea behind it? I'm telling you why it comes into picture. So again, they did something like do everything the RMS prop and delta does to solve the decay problem of Ada grid, plus use cumulative history of the gradient. So this is also doing something similar. Uh, okay, so I think I don't remember why this come after this. So what is the uh, real reason it came? But I can only explain like what is Adam is, right. So adaptive movement. So in this case, we have two things. One is uh, we control the gradients also, and we control learning rate also, right. So like till now, what we see is we have this WT minus learning rate and then this del W, right? So this gradient is there. So what we saw till now is we control this using momentum things, momentum based gradients and nag and all. This we control using eta delta, eta grade, and RMS prop, right? So this is the now I think this is a combination of both of them, right? So we do both of this. We apply eta grade, eta delta also, and we apply momentum also. Yeah, cumulative stability. That's what they mean by momentum, right? So this both thing we want to do, and that's what Adam does. You have this equation. So here you are accumulating gradients, then you What are you doing? You again like doing something with same thing, and but you use it for learning rate. So this gradients are helpful for updates like gradients. Accumulation of history is used for gradient. Accumulation of again gradients are used for learning rate also, right? So these two things now we are doing. One thing here we are using for learning rate, or I'll say as in replacement of eta. Here I'm doing it in replacement of my gradient. Okay. So that's what these two things comes into picture. And now uh, something like what does it called? It's called why we need bias correction, right? So this bias correction is required, and there is a reason why we do this bias correction, and you use it for updating the gradients, right? So that's why this ADAM is a combination of both of them, adaptive learning rate and momentum, also, right? So that's what ADAM means, and now this explanation on why bias correction is needed. I'm not going into that. You can read about it. There are two, I think, sir has proved two ways. You can use, you can maybe go into any one way and then you can set that. I'm not going into that. So now come to what is max prop or RMS. From RMS prop, how we can go to the max prop, right? So let's say you have this value like W1, W2, W3 or something, right? Some values are there. You take L2 norm of this. So you take square of each of them and also take max of that. Okay. Uh, Now, but what if you take infinity of this and then take max of it? What difference does it actually make? Right. So that's what is, where is it? P somewhere. Right? Hello, somebody asking something? Uh, okay. Max. Yeah. Okay. So I think it was here. Yeah. Sorry. So this is first we need to understand what is LP norm, right? So in this case, let's say we have this x1, x2, xp power, and all of them have power p, and you take uh, 1 by p power of that also. So if you see this, uh, what uh, okay. Yeah. So for this case, I guess, like this is the problem where you can take any power of p, but the issue comes with if it is too high number, then issue comes to this. But what if you take uh, infinity to this, right? So addition of this infinity, like x1 power infinity plus x2 power infinity and so on. So in this case, you will get the rest of the values except the highest value. So whatever. So the proof of that is something like you divide each of them by x1 or something like that, and wherever one is there, it remains that only, and rest of them will become zero because they are smaller than one, right? So smaller than one value will become zero. So something like that proof is there. But anyway, so what we need to remember is that if we take infinity norm of anything, whatever max value is in that out of all the values, you get that as output, right? So what we'll do for that, we'll use that and use it here. That uh, instead of using this square, this is L2 norm. Instead of that, we can use L infinite norm. In that case, what we have to do is we can take max value of this value and wt, right? So WT in this case. You will take that and use it for weight updation. So that's what max prop is. Similarly, ADA max. So for Adam, you can do for all this equation. You can do similar thing, and you will get ADA max equation. Okay. Now last comes the NADM. I don't think I will go into NADM as of now. If you have any question, I can take it. But what you are doing similar thing as NAD. You are taking a stop in between. Then you check. You look forward. Is it the right direction to move? If it is, then you move, right? So that's what the NAD did, and same thing NADM will do. Okay, so you take a like a semi step. You should, let's say you must move by this much. That was the full gradient movement was, but you take a hold in between. You stop somewhere. You check the direction. Is it the correct direction you are moving? And then you again move by this much, right? So let's say if it was supposed to move by 1 and 2, so total 3 it should have moved. You move by 1, you check the direction. If it was correct, then you move by 2 in that. If it was incorrect, then you are supposed to move by 2 in the another direction, right? So that's what it leads to faster uh, faster convergence. That's what this NAG did, and that's what NAG will do similar thing with the Adam also, right? So that's what we have. This equation becomes little complex, but it is like this. Okay. Yeah, which optimizers now? Okay. Which I don't think I have to comment on that. Now some decays are there, right? So I think you can look into this decays and all. I hope this is decays and all will be in week 4. I don't think you need to go into that. This part just focus on probably not this 4 5. You can look at the equations and all. Not much difficult to understand the equations. You don't need to remember. We'll give the equation if it is there in the question. Yeah, so that's all there in week 5. If you have a question, you can ask. Okay. Let's probably move to like week 6. I don't know if you have any. Do you have any question week 6? We can take that. Week 6. What's regularization, right? So regularization, I mean, you have any question in what is L2? I think L2 is easily understandable. Like early stopping is there, augmentation of data, parameter sharing, ensemble method dropout is there. Anything specifically in any of this topic you want me to cover? Okay, so do you know what is injecting noise as uh, at input? What is injecting noise means? I'm just asking you.
Just introducing some like error from the original input so that the data is like it's more generalized so that overfitting doesn't happen.
Okay. So okay. And what about injecting noise at output?
I mean, same thing but on the output layer, right? It'll have the same effect.
No, so yeah, so it is L2 normally. So finally, everything is you can see everything. All the uh, things we have seen in this slides are going to end up having L2 regulation. The only difference is here we take the cross entropy part will be changing, right? So that's what we do. Like we take some form of work. So initially, like when we started it, we used to write our true label as 001 0000000 something. Right? So this was supposed to be true label, but now we are injecting noise, so we will subtract some epsilons from this, right? And then we divide whatever the we have taken out as and distribute among all the zeros, right? So this becomes soft target. This is y true in this case, and then whatever y hat you get, you use it for loss calculation, and then you do the back propagation and so on, right? So that only changes. But here in this case, uh, we add some noise in between, right? So uh, for example, here x1 some noise in inputs you add, right? So like Gaussian noise and something like that. Okay. So comes to what is ensemble. So ensemble means what you can what you can do is you can actually uh,
So ensemble is the same as the bagging that we had in ML, sampling with
the
replacement, creating different samples for each models or each trees, so that it gets
yes.
generalized.
Yeah, so it remains same, right? So here it is same as bagging. Nothing changes, right? So you do voting and all. If it's a
Like
classification, it's a
model,
regression.
it's like we are having different outputs. We're comparing the best one and then we're choosing it, right?
Yeah, yeah. Yes. So here it is. I think so. As of now, it's a classification problem. So you take voting only, right? So whatever the majority of them comes out, you take the output. Okay. So same thing here. Now dropout is something new here. So dropout can actually, like it helps you in imitating something similar to ensemble. You can have different architectures, uh, but you don't require multiple architecture to build, right? So since multiple architecture, you don't have to build it. You inherently you can get it. So some nodes you can just remove it, and that's what makes it as a different architecture, right? So, and finally, when all the weights are updated, you use the final model, for example, this with some weights, right? So let's say this were the neurons which were not there while training, but while testing, all of them will be there, right? But you will give that much importance to it only, like it
So the
was like this, right? So that much importance you will give to that value p times p. Here is just remember that there are two things. One is retaining and dropout. Okay, so they always like dropout is what being used generally, but what we have to use this probability p is actually retaining. Okay, so 1 minus p is the dropout probability. So if it is given that dropout is, let's say dropout probability is 0.3, that means you have to use here 0.7 w1 and 0.7 w2 and so on, right? So that's what uh, just make sure that if it's a dropout, then you use the probability of retaining it, right? So that's what you will use. You will not use dropout probability as it is. Okay. I think that's what in week 6. Um, the better activation. I think in this I can do the same thing. So supervised pre-training or greedy pair-wise pre-training is kind of understandable. You take uh, you try to predict the next layer itself, right? So you use that and you predict it, and maybe you take a loss in between and then use it similarly for the next layer, right? So that's what pre-training is. You don't use loss for that, like sorry, you don't use the labels for that. You use the the training value itself, right? So whatever your x1 is, you compare with that what output you are getting. Unsupervised pre-training. Yeah, like here, right? So you had you given x as input, you get some hat as output, but you again compare it with your input only, right? So your input, whatever you got, you compare that and you try to minimize that. Again, you do same thing for the next layer. So now h is whatever this x hat we predicted right here. That x hat is what being used as hij, but now you'll do prediction for h one hat next layer. A similar thing you can do, and you update the weights accordingly to get better results. So that's what supervised pre-training is. What is optimization? Mhm. So some activation functions are there, like so we till now, like this is week 7, so we till now we would have used sigmoid or tanh only, but then there has some drawbacks, right? Like sigmoid is not zero centered, uh, and uh, and it gives like it becomes saturated also after some point, right? So that was a issue with that. So neurons get saturated. If so, saturated means weights are not, gradients are not there. Like gradients are coming zero. That's what saturated is there. So vanishing gradient problem and all are coming into that. To uh, to improve that, some other optimizers, sorry, some other activation functions came here. Is like ReLU came, which is very simple. Then leaky ReLU would be there next. Like okay, leaky ReLU. So ReLU has issue, like there was nothing comes in the left side, right? It is still not zero centered. So if you maybe give some form of some values to here, it becomes very close to zero centered, but and something like that, right? But still, see by far ReLU is still used by most of the real architecture they're using, right? So still, like ReLU is giving good results, but they have found some alternative to it or best to improvisation of ReLU, right? So that is that. Now exponential linear units. So some formula is there, right? So this kind of formula is there for ELU that you can use, and you can see the the graph is coming out to be different, right? So some other thing could be uh, model. You can maybe take average of models, drop out. Okay, so this which drop out like this. It is
You're complete drop out and max out in this, no?
okay. So drop. Yeah, so dropout we saw, right? So dropout layer we randomly or with probability we choose some neuron to remove, right? So that's what dropout was. And uh, what we are doing instead of that we take maximum value from somewhere, right? So uh, you can use some let's say from this four you want to choose something, right? So max of this and max of other, and so on, right? I mean, that's how they have done in the okay, sir has not said it, but yeah, something like this, right? So you use some subsection and then take a maximum value of that, right? So you move on forward with that only. that's what max out will be. And then while doing back propagation, you update this weight only. So, for example, this weight will get updated, this weight, but this weights and so on will not get updated, right? But in that's the next for x2, this could be the maximum value, and that's where this neurons or whatever the weights in between this will get updated, right? So it depends on whichever max value comes here. Uh, whatever max value comes in this hidden layer, based on that you move forward and then you do back propagation for that one. Okay. Okay. So then another like Gaussian error GLU is there and CLU is there, right? So these are just equations. Like if I give you any equation, you can kind of imagine them as a having uh, you can use that equation for activation purpose, right? And then because this is the equation, you can do derivative of that. So they needs to be continuous. That's what only requirement is. If they are continuous, you can take derivative and then you can do back propagation, right? Uh, Automatic search. I think that solve is not there, but okay. Yeah. So I guess that's all is there for the quiz too. If you have any question, we'll go with that. Right? So if you have any question, I'll cover that from week 5 to 8. Yeah. Any questions? Mm. Okay, then we can close it. Thank you.
Thank
Thank
you,
you.
sir.
Best of luck. Close it.
Thank you, sir.
Thank you, sir.